Alright, welcome everybody to week 14, day 1. We're going to be talking about a new topic today, but there are a few more slides on graph theory, and I got the assignment from the Bridges guy, KR, at University of North Carolina. He sent me his assignment last night, so I'm going to go and get that set up for you. I know it'll be very exciting to work with graph theory one more time. We'll keep doing that until the end of the semester, until you guys learn that pattern of doing graph traversal. That pattern of, add all the neighbors to the to-do list, and you pull one at a time off, add all of its neighbors to the to-do list, pull one off, add all of its neighbors to the to-do list. That process, that coding pattern, is crucially important because there's a lot of computer science programs that follow that pattern. Okay? So, the assignment's pretty cool. I think you'll like it. There's a couple more things on graph theory before we get going on the the probability topic. And the first graph theory application is deadlock detection. And so, in multi-threaded programming, you can have these things called locks. And the way that it works is, in fact, I can just show you. There is this thing called a mutex, which is short for mutual exclusion, and the way that a mutual exclusion works is if you have a multi-threaded program. A multi-threaded program means that inside of your program you've got multiple flows of control. Normally you don't have that. Normally you only have single-threaded code. But a multi-threaded program can run into issues. You can run into things called deadlock. You can run into race conditions, things like that. It's actually really hard to write good parallel code, which is one of the reasons why I specialized in it, was because it seemed to me to be very, very useful, and at the same time hard to do, and not a lot of people could do it. So I was planning on kind of making a career out of being the kind of guy that could do things that other people couldn't do. And as it turns out, it was a good career decision, because if you look at how CPUs have evolved over the past 10-20 years, the clock rate hasn't really gone up that much. Like 10 years ago, you could buy a machine with a 3 gigahertz, 4 gigahertz clock rate. Nowadays, 3 gigahertz, 4 gigahertz clock rate, about the same. CPUs really aren't very much faster today than they were 10 years ago. What has gotten better? What has gotten better is the number of cores. Okay, so the Ryzen 9 series has 16 cores in them, which pretend to be 32 cores. And the new Alder Lake thing has a new, I shouldn't say new for Intel design, where it's got 16 cores, but 8 of those cores are high power, and 8 of them are high efficiency. So low power, really. And the clock rate is still in the same range that, it's been for 10, 15 years, something like that. My old CPU, which I had for like almost 10 years. I got it in 2011, and I upgraded out of it probably like, when did like 2019, something like that. 2017. Okay, so I had it for 6 years. Okay. And I've had my current CPU then, I guess, for 4 years, something like that. I don't know if I upgraded immediately. Maybe it was 2018. So I had this probably for 7 years, and then I found my current one for 3. Yeah. And anyhow, so look at the clock rate on it. 3.8 gigahertz. It's the same, right? Like Can we discuss that a bit more in coding? Yeah, sure. I mean, we got a long class today, and this is probability and statistics is the last topic of the class. So I do not mind having a class on multithreading if that's what interests you guys. If you guys want to learn how to do, if you guys want to learn how to do parallel processing, we can do that. So yeah. So what's happened is that rather than our clock speeds getting better, which is what used to happen, like what used to happen was every 2 years or so, there's something called Moore's Law. Every 18 months, clock speeds double. Alternatively, every 18 months, transistor density doubles. What happened was instead of speeds doubling every 2 years or so, we're getting more and more cores. And the trouble with that is that if your program is only single-threaded, in other words, if a single-threaded program will run on one core, then it's really not going to be that much faster today than it was 10 years ago. Okay? Now, the Alder Lake single-threaded performance is pretty good, but it's not noticeably better than, I mean, if you look at the single core performance, here we go. So the core, the single core performance on the 12900 is 400, which is substantially better than the 350 that a Ryzen gets, and it's a good 30% faster than the last flagship product. So it's like a 30% jump, which is actually not bad as far as these things go. Because single core performance has been sort of languishing for years, It hasn't been getting that much faster. Usually every generation that comes out, it's been about 10 to 15% better. And this time they came up with a 30% better jump in performance. So, yay, good on you. Cinebench, let's see, the last one was 1500 and 1900, 10, 20, yeah, between 20 and 30% better, faster. So in order to really unlock the power of these new CPUs, you need to do multi-threaded programming. You need to use all the cores, right? So there's 16 cores, 16 physical cores, and it pretends to be 24 cores to the operating system. This guy pretends to be 32 cores. It's really 16 beneath the hood. In order to unlock all of the power of that, you need to write multi-threaded code. You need to write parallel code. You need to write code that will fork itself or spawn threads. There's a lot of different ways you can do it, and to actively use all the CPU power. Trouble with that, though, is that when you've got multiple computation threads happening at the same time, you can get into contention. Yeah, building a PC is fun. It is fun. So let's talk a little bit about multi-threading. You got stuck on the text parsing problem. Yeah, just post on the help channel, and we can maybe go over the text parsing at some point too. So here's the deal. So let's say that you've got thread 1, you got thread 2. Do you guys know how to spawn a thread, by the way? In C++? No? Okay, we can talk about that in a second. But let's say that I'll just come up with some trivial thing. Like let's say you want to add up all the numbers from 1 to 1,000,000. It's the worst sigma I've ever seen in my life. I'll allow it. Okay, so let's say you're adding up all the numbers from 1 to 1,000,000. If you did it in a single thread, then it would just add up all the numbers for loop 1 to 1,000,000, right? If you did it multi-threaded, what you could do is you could have this person here, there's a better looking sigma, add up all the numbers from k equals 1 to 500,000, and you can have this person add up. That's not as good. All the numbers from k equals 500,001 to 1 million. You guys understand? So you can split the task between two different processors. And sometimes the overhead, because you've got like your main program has to do this, and then these two things have to join back together. So you kind of have your process, it splits into two threads, and then it waits, and they join. This is called a join, because, I don't know, do you guys see why that's called a join? These are coming back together, and this guy will pass in his number, you know, whatever, he'll pass in whatever his number is, and then it'll add up x plus y and return the sum of all from k equals 1 to 1 million. Okay. That makes sense? And you could, in theory, spit out as many threads as you want. And perhaps ideally, the ideal number of threads is the number of cores you have on your system. What's an example of this being used out in the field today? Like literally everything. Like let's say you're doing MP3 encoding. Like you're recording a lecture for your students. And right now it's basically writing down the frame buffer to disk. But let's say later on I want to edit the video, which I rarely do. I pretty much almost always just post unedited video footage. But let's say that I accidentally showed the social security number of all my students or something. I don't want that to go up on YouTube, so I would come into a video editing tool and cut out the part where I accidentally exposed people's personal PID, you know, personal identification. And then I have to resave it as a video file. And so that video encoding is a massively parallel task. And what you can do is you can spawn off you know, thread 1, thread 2, thread 3, thread 4, and thread 1 I could say, all right, you handle minutes, you know, 5 to 10, and you handle minutes 1 to 4, and you handle minutes 11 to 20. You know, I'm making them not even on purpose because they don't have to be even, you know. You might know that this thread is one of the high power cores and this one might be a high efficiency core. And if you know that about the system, then you can give the high efficiency core less work, you know. Yeah, see that? And so you could spawn off different chunks of the problem, and then they all work in parallel and encode the video and save it to disk. Are you guys with me on this? So like, it's really, really useful. Like, not every program is easily parallelizable. If you're doing things like matrix operations, you know, you have like a giant 2D array. What you end up doing is you sort of like divide it up like this. And you run into these issues where, like, if you're like going to be adding up the 4 neighbors, one of the values is going to be like across a foreign border. And so there's some, you know, clever techniques you can do to handle that. Like you set up a thread that will communicate the edges first to the neighbors, and then it does the computation in the middle first. It does the middle part first, while the threads on the edges, there's another thread, a communication thread, handles transmitting the edge data to each other, and then after it finishes the data in the middle, then it does the summation of all the things on the sides, and then it repeats, alternating back and forth between the inner part and the edge part. And while the inner part's working, the communication threads are sending the edge data to each other, exchanging information. And then by the time the inner part finishes, then that part's finished, and then it can do the computation on the outer part. And you can actually maximize your CPU performance pretty well, actually. As long as these things don't get to be too small. You know, anytime you do parallel computation, you don't want it to have like, I don't know, 1 number or something, because then it's like, what's the point? You know? So you want these things to be big, meaty chunks of data. Okay, so That makes sense, Yox Timer? Like, any numerical simulation, you can't necessarily parallelize every numerical simulation, but we want them to be parallel. Let's put it that way. And so people have done very clever work making like a parallel version of matrix multiplication. A lot of linear algebra stuff has parallel implementations. Let's see. Okay, so you can see here that for different operations, I don't know what these stand for off the top of my head, you can run it single-threaded, 2 threads, 3 threads, 4 threads, or sorry, 4 threads, 8 threads, and you can see the performance doesn't go up the way you might expect. Like you might expect that if you're using 8 cores, it'll go from 1,000 to 8,000. A lot of times you don't see that because you have this overhead of having to communicate with the other threads, and that really slows down your performance. So what you see here is that with 2 threads, it goes from like 900 to like 1100. So it's like a 20% improvement from using 2 threads instead of 1. It's not double the performance, it's like 20% more performance. And so with 8 threads, it gets up to like 1500. So it's almost twice as fast with using all that multi-threading. On this one though, it goes from 2700 to above double performance. So with 8 threads, it gets more than 200% speed. So it kind of depends on your task and things like that. But not everything parallelizes well. And oftentimes when you add too many cores, then the performance will drop because you have to spend so much time talking to all of your neighbors that actually slows down your performance. And so when you do grad school and this kind of stuff, you do these kinds of graphs. You run different operations and you run them in different numbers of cores. You run them in different configurations. And you try to find that, what design gives you the maximum performance, right? Because that's what we usually care about in computer science, right? Like, what's going to make it run the fastest? So apparently with 103 degrees of freedom and 32 cores, that's your maximum. Okay. So does the CPU automatically determine how to split it up? Oh, hell no. Most definitely not. The CPU does none of that. The new Alder Lake cores have a have some of that now, but setting Alder Lake aside, basically a CPU is just, I got 16 cores, what do you want to use? And then the operating system says, I want to schedule this task to run on core 7. I want to take this task and run it on core 12. And so a lot of the times one of the cores will be used just by the operating system. If you've got free cores available, then the OS will try to schedule things on different cores. Let's see here, CPU. So you'd see OBS and Wallpaper Engine, which is unfortunate, and Discord are eating up a little bit of CPU time. So you can see these are all the different cores on my system. I have a 20 core system, sorry. And it's not actually 20 physical cores. It pretends to be 20 physical cores. 10 actual cores, 10 logical, 10 physical cores, 20 logical cores. And the thing downclocks itself to avoid wasting power, which is nice. I have 4,900 threads running right now on my system, most of which are idle. So a thread is a different flow of execution. So one program, one process, can actually have multiple threads of execution in it. It's quite common. For example, your networking could be spawned off as a separate thread, And so your networking engine can sit there and talk to the server, and the rest of your system doesn't block. It doesn't wait for communication to go out over the network and to come back. You spawn a thread, say, hey, send this data over to the server, and it just does it on its own initiative. This high performance power setting glibness, if you keep your CPU speed maxed, then yeah, you're basically burning power you don't have to. Because Intel speed step technology will underclock your device quite substantially at times. And you can see it's not underclocking that much right now because I am actually using the CPU to encode this video twice. Because OBS is encoding the screen, as is Discord. So I'm actually encoding my screen twice every frame. And so you can see one of these cores is getting a lot of exercise, and then a lot of these cores are getting just a little bit of work. Out of the 4,900 threads working, out of 271 processes, most of them are kind of idle, and then one core is kind of chugging along, doing its thing. Okay. So memory usage is fine. I'm using 10 gigs out of 32. So, and then you can go up to the resource monitor here if you want more details. And let's go to CPU. And you can see graphs for each of the different CPUs over here. You can see how many threads are running inside of each of these different processes. Dropbox has 156 running, and it's doing basically no work. So basically all of these 156 threads are basically not doing anything. They're just idle. So, my backup system is actually using more of my CPU than streaming video, which is obnoxious. It's actually kind of obnoxious because when it starts backing up, it noticeably slows down my machine, which it shouldn't, but it does. Okay. So if they're doing nothing, why are so many? Well, an idle thread doesn't cost you anything, right? So who cares? Okay, so C++ has this thing called thread, and it's actually really easy to use. Basically just pass it a function, and then that function will run in its own thread. So yeah, like that. And you can pass parameters to the function. So F1 takes an integer, and so you can just pass in the integer here. Okay. So let's just show you how to code that. Thread, I think. Check. Okay, so tell me how many random ints from 1 to 10 you wish to add up. The reason why I'm having it be random is because if you make it just the numbers from 1 to 1,000,000, the optimizer will be like, I know the answer is, and it will eliminate the code. So by making it random, then we can disable the optimization on this, because otherwise the optimizer will eliminate basically all of this code. Is it really that simple? Yeah. Well, the simple part is not creating a thread. The simple part, or the complicated part, is when they need to interact with each other, and that's the point of a mutex, and that's what we're going to get to in a little bit. So So let's just use a global, and we'll use this to show you why globals is not good. So we'll make a vector of integers named vec here, and we'll have a function called int sum up that will take in a vector of integers named vec, as well as size t start and a size t, I'll just call it begin, I guess, to use standard terminology, size t end. So we're going to pass in a vector by reference. Actually, we don't need to. We have it as a global, huh? Yeah, let's not use a global, I guess. That's fine. Begin to end. Okay. And then we'll say for size ti equals begin, I is less than end, I plus plus, so it's a half open code pattern. Starting at vec begin, add up all the numbers to vec 1 before the end, right? End is always 1 after the end of what we want to add up. Okay, so and let's not do an integer, maybe let's do it. 64-bit integer, and okay, so we will make a vector of integers named vec of size. We could do that, or since we're going to be randomly generating it, we'll just do this. Print I equals 0, I is less than size, I plus plus, vec dot push back. We'll generate a random number from 0 to 99, which was surprisingly hard for some of you guys on the snow blind assignment, because all you had to do is generate a number from 0 to 99, and that's how you do it. So you just take rand and modulus it by 100. So this is going to generate a vector of size. Oh yeah, we need to seed the random number generator, srand seed, like that. And then we'll start off by just printing it out, right? So for int x, vec x. How do you make a namespace to shorten it? Yeah, it's pretty common to do this. Using u64 equals uint 64 underscore t. That's whenever I do like game development, it's very common to see u64 i32. And the reason why I like shorting it is because a lot of people use ints just because it's 3 letters, right? And so if, instead of int, if you use i32, it's the same number of letters, but now you're specifying I want 32 bits. An integer in C++ technically could be 16 bits. And so if you ever ran your code on a system that had 16-bit integers on it, which is unlikely, but it could happen, probably your code will break. You know? A 16-bit integer goes up to 65,000. If your game has a bank account held in an integer, and you go to a system that has 16-bit ints, if your bank account goes over 65,000, overflow. I teach game development over the summer. So somebody was asking about static assert. What's the use of static assert? Well, you can static assert that the size of an integer is equal to the size of a int 32. Like, you can do that. And so this will don't compile with ints other than 32 bits. You guys see that? So if you're going to write a large program and you want to use ints and you want your ints to always be 32 bits, you put that in, and then if you ever move to a system that has 64-bit ints or 16-bit ints, the code will not compile, and it'll tell you that. And that's much better. That's a much better way of coding than just using ints and just assuming they're going to be 32 bits, right? It's fine, and on most systems they will be. 32-bit ints is kind of standard now, but it might not be in the future, you know? In the future, who knows what will happen, you know? Computer science is constantly evolving. And so if they ever change the number of bits in an integer, then this will detect it. So your COC is warning on that? I don't think so. Yeah. And this is part of the language. You don't have to include anything. Assert, you have to include CAssert, but for static assert, it's actually part of this the library. Okay, so let's run this code. How many random ints do I want? I want 10. Random seed of 1. Give me 10. Random seed of 1. Okay, so we're getting the same numbers each time. 1, 10 with a random seed of 10. Okay, so we're randomly generating numbers correctly. Now we're going to pass this to sum up, and rather than using a recursive thing, which is what we did last week, we did a recursive summation function. This time we're going to do a multi-threaded one. So we're going to start off single-threaded, which is normally what you do. You start off by making sure you have a working single-threaded implementation, and then you parallelize it. Okay. So we are going to pass to sum up. Do I need to do anything fancy? I don't know. Sum up, passing in vector starting at 0, going to vector dot size. Okay. Remember, end is 1 past the end of the array. Okay. And then we'll just see out the result. We'll make 4 integers. 21, so last digit's correct. 100, 250, 260. Yeah, okay. Good. So it is working. Test it a few more times. $69. 131. Okay, looks good to me. So we've got a working single-threaded implementation. Now let's benchmark this first, and let's make sure we compile it with the optimizer turned on all the way, and we will time main.cc. Time a.out. And we will make 100, 100,000, 1 million, 10 million, 100 million. Yeah, so all that C-outing is going to slow us down, so I'm going to redirect the output to dev null. You direct the output of a Unix program to dev null, it doesn't output anything. Because all I care about really is the running time. And so I've got to be careful here. And 1 million, 10 million, 100 million, and then we'll see how long this takes to run. So it's going to randomly generate 100 million integers into a vector, and then it's going to pass it by reference to a function. It's going to add them up. We do reserve to avoid reallocations. We can do that. Printing out a lot of zeros. Why is that? No, not resize. What am I thinking of? Is it reserve? Yeah, that's what I thought it was. It didn't pop up on my code completion here. Trust your instincts. All right. $100,000. It's taking a long time. Oh, yeah. Helps if you type in the second number, huh? It was just waiting for me to type in the random seed. Okay. And one thing we want to do is we want to not output the number anymore. All right. Time a.out to dev null. Okay. So now we can do some timings. 1 million. Okay. 0.01 seconds. 100 million. 100. Took about a second. So let's do a billion. So we're going to add up a billion numbers now. This should take about 10 seconds or so. Killed. Oh, interesting. How would it die? Killed. It's not going to be integer overflowing. Because the maximum sum can only be 100 billion, which is fine for 64-bit. Why is it dying? Do I have a quota set up? Oh, it's running out of RAM, that's why. It actually can't store that big a vector, is the reason. So, well, we'll just do it with 100 million then. So. No, that's a billion. 100 million. Okay. All right, so our base running time is a second. And we could do fancier stuff like not store it in a vector and just generate the data on the fly, but this is good enough. Okay. So let's parallelize it. You guys ready for this? You guys ready to see how to spawn a thread and stuff? You're like screaming coming from outside or something. Oh, or like wolves howling or something. Okay. Included thread. All right. Strangest sound. Okay. Okay, so rather than returning a value, we're going to make it a void function and have this be a U64 by reference retval. And rather than returning a value, we will do this. You guys see what I did there? So threads don't return values. So if you want to return a value, you pass the parameter by reference. You guys understand? So you guys remember call by reference and why it's important? Why you got to learn in CSI 40? Oh, it's behind the scenes. It's passing a pointer. It's passing a pointer to that, but it just looks like a regular variable. So if you do this, then it's actually writing to this variable here. Yep. So let's just verify this and make sure that it works. .495, 011, 495, 01. Okay. So we're getting the same number. Good. Every time you use the thread, you have to treat it like it's void. Yeah. So, here we go. So we are going to spawn off a thread. Auto thread 1 is equal to thread passing in sum up. I don't know if you guys saw what happened right there, but the first parameter to the thread class is the function run, and then all the subsequent parameters are the function parameters. And so thread will do what's called a forwarding reference. It'll actually forward this and this and this and this. It'll forward it over to this. So these parameters you put in here just get forwarded over to here. And then the first parameter is the name of the function that's going to be run. So when the thread spawns off, it runs this function, passing in these parameters, and then basically, yeah, this would actually be buggy if I ran it like this. Let's do that. That'll be fun. So, static assertion failed. Thread argument is supposed to be invocable after conversion to R values. probably. Does not like that. All right. No. Because the deck is also. Undefined reference to pthread create. That is a linker error. So pthread, and there we go. So 100 million. Terminate called without an active exception. Interesting. Huh. Oh, right. Yeah. I told you it'd be buggy. So, make it not buggy. Let's make it not buggy first, and then explain what's going on in a second. Okay, so we're still getting the same result as before. So what we've done is we've transformed this program into a multi-threaded program. So what we're doing is we're passing in the function name, anything that's called by reference, just due to the weirdness of how C++ is, you have to do this. You basically have to say I'm passing this parameter by reference, and it's just kind of annoying that you have to have that, but you do. So, okay. You don't use ampersand. No, this it's a weirdness as to how like forwarding references work and things like that. So, anything you pass by reference, you have to sort of tag it as this is a reference in order for the forwarding to work properly. Yeah, it's just, it's not the nicest thing in the world, but there you go. Okay. So this is going to spawn off a separate thread of execution. And at this point, our code is now multi-threaded. So we have 2 threads of execution running at once now. Main, and then thread 1. Okay, so I could do things over here. I could see out waiting for the threads to finish. And so you can see that the main thread prints this out, and then after the thread 1 finishes, let's do this with it. End line. Then it, once thread 1 finishes, then it prints out the result. Okay. So this CPU, well, the system we have here on the server isn't very parallel. It's got 2 cores running. And so this isn't a very multi-threaded system, and the way the thread scheduler works is that it very rarely will you see any thread performance increases, but let's give it a shot. So is this really much faster than the previous one? Not really. I don't think so. This is exactly the same as before. It's just we're doing the computation in a different thread. It's not going to give us any speed benefits, right? So if we time a.out, we'll see that it takes the same amount of time as before because we're not doing any parallel computation. It's a parallel program now, but main is just sitting there like twiddling its thumbs. All main is doing is waiting for the thread to finish. So it's not doing anything. It goes idle, basically. Yeah, main goes on break. And that's pretty normal. Usually your main thread just spawns off a bunch of threads, and then it just waits. And it waits for them all to finish. So that's, yeah, that's pretty normal. Isn't some still running a billion numbers? Not a billion numbers, because we're running out of RAM, actually. We only have 2 gigs of memory on the system, so, yeah. So we're only doing 100 million. And I could get around this, but it's too much of a distraction from the point. Okay, so now let's do 2 threads. Okay. So, beginning to halfway. You guys see that? So the first thread is going to take the first half of the vector. So from 0 to halfway. And then the second thread will go halfway to the end. And this, because it's the half open code pattern, these two are the same. You don't have to have like a +1 or a -1 in there. You just use size, and it knows to go 1 less than the size. That element there at n-2 isn't actually added up, but it is added up in the second thread. Can a thread run a thread? Sure. Yeah. That's why not. And so we've got these 2 things here, and both of these guys are going to be writing the results to result. So this is now a buggy program. Doesn't look like it's buggy. And in fact, I'm willing to bet dollars that we might actually get the same result as before. 100 million. Woo. Yeah, because we didn't have a join. Sorry. Thread 2 join. And whenever you compile your code with multi-threading, you need to add that compiler flag, -pthread. It's pretty common. A lot of programs like Bridges requires you to compile with -pthread on. 100. We did not get the right answer. See that? The execution time actually took longer than before. Even though we have 2 threads running in parallel, the execution time actually took longer. Okay. And the reason for that is just because of the server. The server is not parallel. It just really isn't. It appears to be a 2-core system, but I think it's actually 1 core with 2 logical cores on it. I don't think parallelism will not show any gains on this, but it will show that we did not get the correct answer. Okay? You guys see that? Why? What happened here? Why did we not get the right answer? Got the right answer now. What did I change? I moved the join up here. Join means wait for thread 1 to finish. So if I spawn off the thread and wait for it to finish, and then spawn thread 2 and wait for it to finish, it works fine. But if I have them actually running in parallel with each other, if I have them running in parallel with each other, then I don't get the right answer. Why? So think about it. What are they reading and writing to over and over again? Yeah, AJ has the right answer here. They're both reading and writing to the same variable at the same time. And that's a problem. That's why we have mutexes. So what's going to happen here is we get something called contention. Okay? And this is the bane of parallel processing. If you are reading and writing to the same variable, then you got problems. So if you have thread 1 and you got one variable here called writeVal, right? You got thread 2. And so let's say that you're just going to do a writeVal plus plus just to make things easy, right? We're just going to be adding, they're both going to be adding 1 to writeVal. Now let's say writeVal equals 10 right now. So T1 executes writeVal plus plus and T2 executes writeVal plus plus. So thread 1 loads the value of writeVal, 10. And let's say thread 2 loads the value of writeVal, 10. And then T1 adds 1 to it, so it's now 11. And then it stores it back. So this variable over here turns into 11. And then this guy changes 10 to 11, and then stores it back into 11. So what we've had is 2 plus plus operations, but only one of them actually did anything. The second one. The first one overwrote the value of the second one. It did not use this value, it overwrote it. Do you guys understand? So because these are not what are called atomic operations, an atomic operation cannot be divisible. And there's a whole C++ library called atomic, if you're curious about that. And then that provides support for plus plus. So you can do an atomic increment, or you can do an atomic plus equals operation. Okay. So we're not doing that though. So we got a regular variable here. We're reading, we're writing to it. A problem. Okay. Do you guys see why there's a problem? If you're reading and writing to the same variable, and the read and the write can be done separately, then you can read and the other person writes to it, and then your read value is out of date, and then you write to it, and maybe they just read from it, and you sit there and you just overwrite each other's values left and right. Do you guys see the problem with this multi-threading? Or is it too advanced? It's a very common problem in multi-threading. It's the problem, really, other than deadlock. Okay. So, let's talk about mutexes. So mutex is stands for mutual exclusion. And so if you have a line of code that only one thread should be in, you use a mutex. Okay? So it's like I don't know, like it's a good metaphor. It's like one of those pay toilets, right? Only one person can go in at a time. And so if somebody's in the pay toilet, then everybody else has to wait outside. And then once the person leaves, now the pay toilet's available and somebody else can go in, right? And then it locks. And as long as the person's inside of there, nobody else can get in. That's basically what a mutex is. It's a system that only allows one person into the porta potty at a time. You don't want to have 100 people in there. It's going to get very dirty very fast. Okay? So maybe this is because I was playing Borderlands 3 last night, and there was a quest in which there's a person locked in a porta potty. Maybe that's where that metaphor came from. I don't know. Okay. That's how unpaid toilets work also. Yeah. So, yeah. So let's do simple lock. Okay. Not really using Chrono right now. Okay, so Mutex stands for mutual exclusion, and you can say Mutex Bob porta potty. I don't know. No, we'll do Bob, whatever. Okay, so we've got a Mutex named Bob, and then prior to reading the ret val here, we do what's called a lock guard. I wonder if it'll work without it. Yeah. Okay, so what this does is this is a variable named bobguard of type lockguard, and what it does is it tries acquiring the lock on Bob. So it's like, is the porta potty open? If so, go inside and lock the door. That's why it's called a lock guard. If nobody is inside of the porta potty right now, it goes inside, locks the door. And then when it leaves, when Bob guard goes out of scope, there's a destructor on it that unlocks the door. So when they leave, the door automatically unlocks. And then then the next iteration through the loop, it'll acquire the lock again. At the bottom of the loop, it releases the lock. So this is highly inefficient code, by the way. Because what this is going to do is it will, at every iteration, 100 million times, it is going to acquire the lock and release the lock, and acquire the lock and release the lock. Okay? So this is not how you should structure your code, but it will be educational. So we'll compile this. Missing template. Okay, fine. This is a Mutex lock guard. 100. Let's time this actually. 100 million. Look at that performance. Look at that performance. Bro, that's a nightmare. Yeah, so the performance dipped from about a second to 4.5 seconds because 100 million times it acquired the lock, released the lock, acquired the lock, released the lock, acquired the lock, released the lock, acquired the lock, released the lock. Okay, but we got the right answer. You see? So this is the problem. This is the core problem in parallel processing, is that if you are ever reading and writing to the same data, the cost of synchronization, of making sure that you're not stepping on each other's toes, oftentimes overwhelms the benefit of the parallelization. Okay? So you wouldn't want to write code this way. And there's a lot, and you know, this is why I got a master's degree in it. Because there's a lot of tricks you can do to get around this problem. Okay? So the most obvious trick, is to, well, we can do this, right? Like we can acquire the lock prior to the loop, right? You guys understand? So we just acquire it, then we loop over it 500,000 times or whatever. But now, it's not parallel anymore, right? Because what's going to happen is that one of the threads acquires the lock on result, and it does its thing, and after it's done, it releases it, and only then will the second thread run, right? So this is back to being a parallel implementation, just worse. So you can see the running time is still a little bit worse. Okay. So this is also not a good implementation. So what I'm going to do instead is this. It's not in parallel, it's in series, yeah. Because what this is doing is this, only one thread can be in this for loop. That's what this line of code here is saying. So it is protecting this for loop. Only one thread can be in this for loop. And that's pretty common. Like if you're going to be writing to disk or something, and you're going to be writing out like, 1,000 numbers to disk, you don't want two people writing to disk at the same time because the numbers are going to go like this, right? It's going to be a complete disaster. And so if you have some code that needs to happen, like this for loop has to finish and then you can do it, then that's the code you write. You do a lock guard and then take the lock and then do your thing. And then when the destructor is called, which is called here, Bob guard releases the lock on the for loop essentially. And then another thread can come in and do it. So what is the right answer? Well, how about this? How about that? So rather than both of them writing to the same return value, why don't we just give them their own chunk of memory? And if they have their own chunk of memory that they can sum up into, then there's no contention. And this is a very, very common solution where you just give each thread its own variables to work with and they kind of do their thing, right? It's anytime you need to have threads communicate with each other that you have to start worrying about mutexes, and we don't need this anymore. Why? Because retval is two different variables now. One for thread 1, one for thread 2. They're no longer hammering the same spot in memory, overwriting each other. So we have to have main do one add at the end, and that's fine. That's not going to kill us. Do you guys see the solution here? Sacrifice space for time. Yeah, it's very little space. We're talking, what, 64 bits? Yeah, whatever. So, yeah. And so giving a thread their own variables to play with so they don't have to synchronize when they don't have to, common approach. But sometimes they do have to synchronize, Sometimes they have to, read and write to some variable together, and then you have to use mutexes and things like that, or atomic operations to do it. So here we go. So there you go. Our fastest implementation yet. Here, I'll put it up. I'll put it up for you, Docslimer. So copy main.cc into public parallel.cc. Okay. So there's the code. And parallel programming is hard. It's hard not because it's hard to like spawn off a thread or something. I keep editing on Discord. Delete Discord message. What's hard is not this bit, like the spawning off of a thread and the joining of a thread. That's all pretty easy, right? Like, do you guys see how easy it is? You just spawn off, like, I don't know, like you could have like a function called like, I don't know, triangle print or something. And just have it do like for int I equals 1, I is less than 20, I plus plus. So like if I just wanted to like spawn off a thread You know, you like auto t3 equals thread triangle print. And so this will just spawn a new thread. It'll spawn a new thread, that we'll call this function. And so this function will run just at the same time. So these guys are doing their business. They're like adding things up, and then triangle print will just run at the same time. You know, so t3.join. In fact, I'll put this up here. So triangle print will run, and these guys add up their things, and you just have things kind of happening at the same time. It's very easy, right? You just create a new thread, pass it the name of the function, and then that function runs on its own thread. And you have really no control over when it gets scheduled. That's up to the operating system. So the operating system will look at the number of threads you have and determine when they actually get CPU time. Okay. And what's probably happening here is that it's just scheduling thread 1 first, is my guess. So my guess is that these CPU intensive things are running prior to this one. That is calling a flush, so I don't. Yeah, looks like the triangle print isn't running till after the other two threads have finished, which, you know, it's prerogative. Guess I could do that. Make it print first. Never mind. Maybe it's just an artifact of the printing. Either. Okay, so yeah. But do you guys see that? So that's what you do. You just say thread, pass it a function name, and that function will run in its own thread. And then you join it later on to say make sure that it's finished by now. And if it's not finished, it waits until it's finished. Thread. Questions about this? The only dicey bit is this bit, all right, where you have to tag call by reference parameters as refs. That's the only bit that's kind of irritating about it. Your code runs slower when it's multi-threaded than single-threaded, or just in general? Are you on your own server, or are you running on the server? Just in comparison to yours. Are you doing 100 million? You're on the server? Are you doing the reserve? This is a nice performance optimization there. So it keeps the vector from having to reallocate. Right. Let's check it out. Interesting. Took 5 seconds. Yeah. Let's see. What's the name of the file? Thread? Okay. Yeah, so did you compile your code with the optimizer on? And did you unalias G++? Because by default, all you guys get a slow and safe version of G++. Whenever you type G++, it does all this stuff for you behind the scenes. So it turns on the safe standard library. That thing there. So it does lots of extra bounds checking and sanity checks and things like that. It turns on the address sanitizer and the undefined behavior sanitizer. Those slow you down a lot. So the warnings don't really matter at all, but the address sanitizers will definitely slow you down, and then the safe standard library will also slow you down. So yeah, you can see it's a factor of 5. And the reason for this is because when you're doing development, safe, you should always start with safe and then move to fast once you're confident that your code is correct. So, yeah, good lesson. My CSI 40 students are learning that right now about the power of the optimizer and speed penalties. Like, Azure Sanitizer for their project slowed it down by about twice. It's about double the slowdown. Okay, so I think this was a pretty good introduction to threading, multi-threading, using mutexes to protect common code. It's not really hard. What's hard is avoiding contention. You know, like because this was easy to resolve. We just gave them each the return value, right? That was an easy solution. A lot of parallel processing things don't have an easy solution. If you're working on a 2D array, and you're reading values north, south, east, and west of you, north of you might be your northern neighbor. And so if you're reading and writing to that, if you're reading from it at the same time they're writing to it, you could get a wrong value. And so, like I said, you have to spend some time, like, all right, I'm going to have a communication thread. The communication thread will send my top row, gets sent to my northern neighbor and reads their bottom row. And so they send me data, I send them data, and then we lock that data. We use a mutex and make sure that nobody can touch it. And we exchange hostage exchange across the DMZ. North Korea, South Korea, they trade whatever data is in that row, the bottom row and the top row. They exchange the data, and then you run your computation. But because that takes time, and you have to do that north, south, east, and west, what we typically do is we have a computation thread, and the computation thread runs on the inner part of the array, and then when that finishes, it checks to make sure the communication threads have finished their work exchanging data along the borders. It's called overlapping execution and communication. So you have one compute thread and one communication thread per chunk of this giant 2D array. And that's a good solution. Something my professor was really good at. He's now at Berkeley, by the way. I got lunch with him a couple of years ago. He was offered a lab at Berkeley, and I was like, well, why did you leave UC San Diego? It's like, it's Berkeley. I was like, all right, it's fair. Yeah, fair enough. They offered him a high-performance computing lab at Berkeley. No, it's fair. Okay, so let's go ahead and take a 10-minute break, and when we come back, we will probably talk about Deadlock or something. Yeah, we can do that. All right, 10 minutes. Come back at 11:35. We go over the daily quiz? Sure, we can do that too. All right, so welcome back. I just played the Atom Bomb Baby trailer for Fallout 4. Yeah, Fallout New Vegas, I think, was definitely the best Fallout game ever made. I'm not just saying that because one of my friends was part of making it. Fallout 4, yeah, it had nice graphics, I guess, but the story, not even the story, it's really just how linear all the quests were, was really off-putting. I just didn't like how they designed the leveling system and the class system, and there's only one choice you make in the entire game, which are the factions you support, and that's it. So I hear people are remaking Fallout New Vegas in Fallout 4 using the engine. We'll see if that ever materializes. Because there's been a lot of efforts like that, like Skywind and things like that, to remake Morrowind and Skyrim, but it's a lot of work. It's a lot of work to make a game like that, so they typically languish for years and don't go anywhere. So the reason why I mention that is because during break I implemented a atomic implementation of the same thing. So we've got here a variable called atom bomb baby, initialized to 0. And this is an atomic U64. So every time you do an operation on it that it supports, which is not a lot, you can make sure that it is an atomic operation. So you can do plus equals on it, and that ensures that the reading and the writing take place at exactly the same time. So there's no ability to split it like we did here, where you read one value, you read a value, you write. Not possible with an atomic. With an atomic, you just say add 10 to that, and the thing adds 10. You can't split the reading and the writing of it. So downside, let's see here. Let's turn that part off. So the downside is, look at that performance time. Skyrim's having its 10th anniversary in 2 days. Wow. Yeah, I remember when that came out. My friends came over and they're watching me play Skyrim. It's pretty fun. Man, it's been a while. And they still haven't come out with another game. It's been 10 years. What's up, Bethesda? Come on. They've just re-released Skyrim like a half dozen times now. So you can see we're getting the correct result. But look at that performance. That performance is not good. Yep. It's 3 times slower. So, trying to fix Fallout 76 still. Yeah. Disappointing. So, with atomics, you can have both threads reading and writing to the same thing. But, I don't know. It's 300% slower. They finally announced Elder Scrolls 6. But Hammerfall? It's got to be Hammerfall, right? Oh, no, this is the one from E3. Yeah. 3 years ago. Terrible. Absolutely terrible. Yeah. Okay, so that is that. Now, let's hop back over into the presentation. And there's this thing called Deadlock. And so this is the other major challenge when working with parallel processing. Let's say that you try to acquire a lock and somebody else has the lock. Then you wait. Okay? But what if they're waiting on you? What if there's 2 locks? I take the first lock, you take the second lock, then I try to acquire the second lock, and you try to acquire the first lock. You guys see the problem? It'll hang. It will create an infinite loop, essentially, that will do nothing. Entanglement, yeah. And so you can use graph theory, though, to detect that, because what happens is you've essentially created a cycle, right? So I've got 1, I'm trying to acquire 2, you've got 2, you're trying to acquire 1. You see how that kind of like conceptually forms a circle? So, yeah, exactly. So, you guys understand? Like, it creates a cycle. And so you can use a graph theory algorithm to do cycle detection. And so basically, if you detect a cycle on the graph, on the left-hand side, you've got the threads. On the right-hand side, you've got the locks. And basically, yeah, if you ever detect a cycle, then there's a deadlock, and you have your locking system or whatever kill the program or throw an exception or whatever. Break the deadlock. Okay. Yeah, Spider-Man. Office pointing memes. Yeah. Okay. You guys understand? So there's code that can detect a cycle. And then you just have whatever it is that's handling your mutexes. Every time you acquire a lock, you just check to see if there's a cycle. And if there is, throw an exception or something and let the system reset, basically. Okay, and now here's another graph theory thing that's kind of fun. It's a game of Ingress, and so it's the game made by Niantic. Niantic is the people that make Pokemon Go. before Pokemon Go there's Ingress. And what you do is you go to a Pokestop, it's what's now a Pokestop, and you capture it for your team. And there's Team Green and Team Blue. And what would happen if and then you draw a line between them. So after you capture a Pokestop, you can connect 2 Pokestops, 2 portals, what they call them, with a edge. And if you ever encompass a triangular region like that, then it shades all of it in for your team. And you get points based on how big a triangle you draw. And this is in real life, mind you. This is in real life. This is not like people go into the game and they're like, where's my controller to move my person around? There is no controller. You walk. You know? So you walk. And so, like, for example, I would go over to the Woodward Park Library, capture the portal there, then drive over to Audubon, capture portal there, drive up to, I don't know, Millerton, capture portal there, and then link them together. And it would create a triangle virtually overlaying the entire area and score a bunch of points. And I had friends that would go up into the mountains, you know, like, I went to Hume Lake. There's a portal at Hume Lake. And so you like go out here to Hume Lake and you connect that to, you know, let's say this is Millerton. This is like Woodward Library. And you get points based on the area. So you want these things not to be close to each other because then it's just like a little sliver. And this would be like Audubon or something. And then if you connect Hume, it's up in the Sierra Nevadas, then you get a giant amount of points for it. Yeah. The trouble is, like, none of the lines can overlap each other. So if an enemy takes a point up here, like a Yosemite, and they capture a point down here in Sequoia, if they link those things together by a line, you cannot do this. Lines cannot ever cross, geographically speaking. So what you have to do is you call up your friends down in, you know, the Sequoia region, tell them to go blow up this portal, have friends go up to Yosemite, blow up that portal, and you clear all the different blocking lines, and then you go and make these giant triangles. And so I had friends that like went out to the Catalina Islands, you know, off the coast of California, because there's a lighthouse there that's a portal, and then cleared all the blocking lines across San Diego County, and they captured a portal up in the middle of the mountains in San Diego County somewhere. And then the northern point was in, I don't know, or Mojave Desert somewhere. And they just created this massive, you know, triangle that just overlaid like a big chunk of Southern California. And you can't, if you're within one of these areas, you can't actually do anything. You can't play the game. Once you're within a triangle, like if you're, you know, if they draw a triangle like over like California, like you can't play the game. Like you can't draw any lines. You can't you can't do anything. And so people would do these big operations where they would clear all of the links, you know, and then basically just drop a triangle over all of California. And it basically shuts down all play in California. This is not great game design. Like, it is not a well-designed game. Niantic has never been accused of being able to make a game with good game mechanics. Okay? Pokemon Go is a garbage Pokemon game, right? So, are people still playing it? Yeah. In fact, I don't, but it was good. It was a good exercise. Like, I used it as an exercise app, just like how Pokemon Go is a good exercise game. It is a garbage Pokemon game. It is a garbage video game. But it is a good exercise app. It gets you out. It gets you walking around, you know, things like that. Oh, there's a Snorlax over there. I'm going to go run over there and catch it before it despawns, you know. Captured Soul Tower, yeah. It's a mobile game, yeah, where you literally have to walk around. And the nice thing about putting things like up at Hume Lake or something like that is that when it's wintertime, it shuts down. Right? And so nobody can get there. And so it's your portal, and then all you do is you just go over to, you know, you go to like Clovis, and, you know, and you can make these huge triangles all connected out of Hume because it's winter and nobody's there, and so nobody can retake it. So, like, prior to winter setting in, I would like capture points up in the mountains, you know, and you know, like North Fork or something, and you know, you just make these huge triangles and get tons of points, and nobody can do anything about at least the ones up in the mountains because it's inaccessible. Right? So. Do the servers constantly crash? I don't remember them crashing. So yeah. So Niantic was a branch of Google, and they spun off their own company to do that kind of stuff. So the question for you guys is, by creating an edge, how many triangles can you create? Okay. So if you've got point here, point here, point here, this is not a triangle. It doesn't count. So with one edge here, I've just created one triangle and two triangles. So the question that I have for you guys, and you can talk about it. I'll pause the recording for a few minutes. There's a limit of the highest degree a graph can have in Ingress is 8. So no point can have more than 8 edges coming out of it. Okay. Can we draw it and send a picture of it? Sure. Right. So I want you to think about this, and think about, with one edge, like laying down a single edge, how many regions can that create? Okay, here's an example of 2. You're going to actually have to show it to me. Don't just say 8. I don't know. It seems like 8. I don't know. I actually draw it out. Show that by laying down one edge, how many triangles can you make? Okay, I'm going to pause the recording now. I want you guys to think about this. Are you using your example? I mean, my example is 2, but I can tell you that you can do better than that, right? So think about it. How many triangles can you create with one edge added? Here would be an example of 1. Right? Okay, I'll pause the recording. All right, so we'll start recording again and take a look at some of the solutions. So let's pull this over here. So yeah, if you had this graph here and you added this line here, it would only create a single triangle, this one. The reason for that is that even though this vertex here is coincident on the line, it's not, the edges connect 2 vertices. Remember, the actual definition of an edge is something that connects 2 vertices. So technically, even though these vertices are coincident on the line, they're not on the edge. The only ones that are on the edge are this one and this one. So it would create a single triangle holding this. This one doesn't work because lines can't cross other lines in Ingress. Remember we talked about a blocking line. So if you have a blocking line, you can't throw another line across it. This one doesn't work because even though, yeah, sure, you drew a single line, this is actually a bunch of different edges. There's an edge from here to here, an edge from here to here, an edge from here to here. So that one doesn't count for that reason. This one, same thing. It's connecting this vertex and this vertex. So even though there's vertices here coincident on the line, they don't count. Yoxtheimer has the correct answer, which is you make a bunch of unfinished triangles that share the same vertices on 2 of the points and are different on the 3rd point. And then you finish the last leg of all the triangles at once. So by drawing a line like that, then it will create all of these triangles simultaneously. And the other one I saw that worked was Alapizco's, which is this, and this is, yeah, how you do it. In fact, that's how it's done in the game. Like, if there's The way the game works, it's not just on the size of the triangle, but it's also on the population density in the area. And so if there's like a downtown area or something that's got a ton of people in it, then that's actually worth a lot of points. And so like, let's say that there's like this downtown area and it's worth a lot of points, then what they'll do is they will do this. They'll overlap it, but they won't finish it. And then they do this. And then they do this. So they just find a bunch of portals, you know, vaguely in the same direction. And if you're in a dense area, they do that. And then after they got a bunch of them lined up, then they connect these here. And then this area scores not just once, but 7 times. So if there's an area that's worth a huge number of points, they will score it over and over and over again by making overlapping triangles covering the same area. Because normally you can't do that. Once you've got an area filled in, you can't really do much with it, right? So this is a very common technique to score multiple times. I think if you did this, you could probably make this one and overlap it again. But by doing this, you score it all at the same time. So the triangles overlap is fine. Yeah, the triangles can overlap. The lines can't cross. Yeah. Although I did once see a bug where I had this, and the game bugged out because this should not be possible due to the overlap. That was over by the GB3 North gym. And I took a screenshot of it, and I'm like, I'm pretty sure there's a bug, guys, and it was. It shouldn't have been allowed. Okay, so let's talk about a new topic. So let's talk about probability theory. Yep. So probability theory has its basis in gambling. Okay. So if you're not a gambler, don't worry. You don't have to become a gambler, but you know, your basic 6-sided die, 1, 2, 3. You know, like you've seen a little 6-sided die. It's got a 1, 2, 3, 4, 5, 6 on it, and ostensibly a 6-sided die should have an even chance of rolling each of these different numbers. Usually, they're not well balanced. Got my bag of D&D dice over there. But like if you stack up your dice and then you rotate them and stack them up again, they're not going to be the same height. Like dice are actually very rarely made to precision standards. There's a company called Game Science that creates the world's most accurate dice. And they're like laser cut, and they're actually painful. like they're actually so sharp they actually hurt your hands to roll the dice. But they're the most accurate dice in the world, and they'll color in the faces for you if you want. So I have a set of Shadowrun dice, the 5s and 6s colored in from them. So so the basis of probability theory comes from gambling, and that's why you'll see in the literature a lot of, you know, gambling references. But if you don't gamble, that's fine. It's the general principles of probability theory are widely applicable. Anytime you have a random event in reality, you know, people will probably try to study it using probability theory. Okay, so let's go through some terminology first, right? So if you have an event is like rolling a die. Okay, that's the event. It's rolling a die. You're generating a random number. Okay. Then you have an outcome. And the outcome will be a member of this set here. 1, 2, 3, 4, 5, 6. Can you imagine? They're expensive. They're not super expensive. They are more expensive than regular dice. Yeah, stepping on them does hurt. They are actually hard, and they're very, very sharp. But they're precision instruments that you should not be leaving on your floor anyway. Yeah, it's like 20 or $30 for a set of dice, something like that. Yeah, so I bought 20 D6s from them for a Shadowrun. So that would have been probably about 50 or $60 I spent on those things. Yeah, and they have the 5s and the 6s colored in one color, and the 1s colored in another color. Because in Shadowrun, 2s, 3s, and 4s don't matter; they don't count for anything. So what you do is you roll your dice, you count how many 5s and 6s you got. That's the number of successes. And then 1s are kind of not used, but if the number of 1s you roll exceed the number of 5s and 6s you roll, then you fumble. And so it's like a critical failure. And if you fumble and you fail your dice check, then it's a critical failure. So a fumble means like you're shooting, you hit, but your gun jams. A critical failure is your gun explodes in your face. And so, yeah, by having them manually color the faces, you can just roll in and be four successes, 2 failures. Okay, that's a hit, you know. So, seen D100s that cost more than that. Yeah, they're not bad. They're not bad. Okay. So the outcome would be a number from 1 to 6. Okay, so the event, you roll a die. The outcome, the number is 1 to 6. Okay. So some people call this the field of possible outcomes. So, you know, look at what possible outcomes you can get. You can get a 1, 2, 3, 4, 5, 6. Sometimes people call this the sample space. Okay, there's a lot of terminology in math, and none of it is really that hard to understand once you understand it. But it's the point of getting to the point of understanding it that's hard. So I'm very anti-jargon and anti, you know, saying big complicated words to make me sound smart. So it's not. I don't have any interest in teaching in order to make myself feel good. My purpose in teaching is to teach you guys, to have you understand it. You know, when I solve programming assignments, it's not to flex on you. It's to show you how an experienced programming dude solves problems. You know, so. And Shahab, I know, wants to do Type Racer against me, which we will get to. We will get to it. Okay. So every time you roll an event, roll a die, that's an event, and you get an outcome from the field of possibilities. Right? If you roll the die, you get a 3. If you roll the die, you get a 5. If you roll the die, you get a 1. And so the probability of an event is the you basically write down how likely is it you're going to get a 1 or a 2 or a 3 or 4 or 5 or a 6, right? And in theory, each of these should be like 1 out of 6, right? If you have a fair die, the probability of getting a 1 should be 1 out of 6, right? In reality, a lot of dice are unfair. And as the game science people show, like, they're not even the same size in the different dimensions. So, I don't know. I know I've had students request we do more video games together, kind of like what we did for the Halloween party. So, I don't know, maybe in a week or two we'll do it. So. Okay, so there's a couple different ways you can notate. There's a couple different ways you can write down the odds of getting a certain number, like a 1 or whatever. Like I usually write it like this. I usually write it as 1/6, because, you know, out of every 6 rolls, one of them will be a 1. You know, you can say 1 out of 6. You can say 0.16. This is converting decimal, fraction, decimal, right? 16%. Now, this is quiz question. Okay, and we will talk about the quiz in just 1 second. So how 5? I thought it was a 6. Okay. So whenever you go to like horse races and things like that, they'll say the odds on this horse are 4 to 1, and so that means that it will lose if it's 4 to 1 against the horse, which it usually is. It's usually not 4 to 1 for a horse. That would be a really good horse. But usually there's 4 to 1 odds given against a horse, right? And so if you're going to bet on the Kentucky Derby, here's a horse. There you go. Here's a horse. He's number 13. There's a horse. My little pony, my little pony. Okay, so we have here Twilight, Sparkle, number 13 in the Kentucky Derby, and there's 4 to 1 odds against. That's how against. That's how it's reported at a betting track. Okay, I've only been to a calling steroids on that horse. Yeah, it's got like this lump of something. I don't know. I don't know what's going on there. I'm gonna fill that in. There you go. It's part of the mane now. There you go. There. Much more beautiful now. Okay. So if there's 4-to-1 odds against this horse, what they're saying is that it's going to lose 4 times more often than it wins. Does that make sense? So like, if you have 5 races, 4 of the time they lose and 1 of the time they win. So 4-to-1 odds is a ratio. That's what the colon means. The colon means ratio. So it's going to lose 4 times more often than it wins. And so if you think of why this is a 6 and then why that's a 5, if I ask you, what are the odds on rolling a 1? Well, it's 5-to-1 against. 5-to-1 odds against it. Because 5 times you're going to lose to every 1 time that you win. Right? So you get a 1, you win. You get a 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, you lose. So there's 5 opportunities for losing. There's 1 opportunity for winning. So it's 5-to-1 odds against rolling a 1. Okay. And so that's a great quiz question right there. Like, between fraction and odds calculations is something that always confused the hell out of me. I'm like, why isn't it 6-to-1? It's got a 1 out of 6 chance. Yeah, that's not what it means. I mean, it's a ratio. So you lose 5 times more often than you win. And so you convert by, like, I don't know, subtracting 1 or something. I don't know. Okay. All the probabilities for an event must be between 0 and 1. Until you get to quantum mechanics. Different story. But yeah, all probabilities have to add up to 100%. Okay. So you have 1 out of 6 chance for a 1. You have a 1 out of 6 chance for a 2. You guys understand? ... Up to 1 out of 6 for 6. So if you add up all the different probabilities, it adds up to 1. Okay. So if it was 2-6, it would be 4-to-2 odds or 2-to-1 odds. Yeah. So yeah, what are the odds of getting a 1 or a 2? Right? It would be 2/6 in probability terms, which is the same thing as 1/3. You have a 1 out of 3 chance of rolling a 1 or a 2. And then your odds calculation would be 2-to-1 against. Or 4-to-2 against if you don't believe in simplifying. If you don't believe in simplifying fractions. Right, because there's 4 numbers that cause you to lose. There's 2 numbers that cause you to win. 1 and 2. 3, 4, 5, 6. So it's a 2-to-1 odds against you. Okay. It's just the ratio of winning versus losing. Okay, so if you ever do your math and you find out that you have a 120% chance of winning, you've made a math mistake somewhere. You know what I'm saying? So all the probabilities together have to add up to 1. And if they don't, you've done your math wrong, or maybe you've gotten a floating point error, which happens. That's one of the worst things, because like when you're working with like, wow, that's a big thing, like 1/3 plus 1/3 plus 1/3, what does that add up to? The bet was just that good. Yeah, give me money and I'll invest in the stock market for you. 120% returns guaranteed. Have you ever seen people say something like that? Should immediately set off your scam warning. If there was ever a guaranteed investment that would always pay off, people would make that bet an infinite number of times, right? And make an infinite amount of money. There cannot be a guaranteed win on the stock market. So what is 1/3 plus 1/3 plus 1/3? $99. No, that's way off. Yeah. 100. Did you guys go to like Fresno Unified or? I'm kidding. I worked with them for years. Okay. So, it should be 1, right? It should be 1. But yeah, I worked with Fresno. Actually worked with all the school districts in Fresno, Madera, and Kings counties for 7 years or so. It's good-natured ribbing. All right. On a computer, though, this is going to be about 1. Okay? Because, yeah, rounding errors, right? Whenever you work with a float, that last digit isn't guaranteed to be correct. So every time you do a floating point addition, there is a possibility you do not get the number you thought you were going to get. So if you add up 1/3 3 times, you might end up with 1. You might. Or you might not. You don't know. It'll be 1-ish. It'll be 1-ish. So, you know, that's one of the downsides to that, right? If you hold these probabilities in decimal form, then you have to be aware that your numbers might not add up to 1. And so typically what I do is if I've got 3 events that are 1/3, 1/3, and 1/3, I roll a die and I generate a number from 0 to 1. And I subtract out the 1/3. So if I rolled a 0.4, I'd subtract out 1/3. And if I get a positive number, then I don't do this one. Then I move on to the next one. Then I subtract out the odds for that. Does this sound like the Markov assignment? Yes, it is. So then I subtract out the 1/3, and I get a negative number. Cool. So this was the event that fired. So event number 2 fired. And then for the last one, I don't subtract anything, and I just do it. So that way I never have the possibility of nothing happening, right? And so whoever is last in line will pick up that, whichever is the last event will get a very small advantage, right? I'm not making a casino game. I don't care. I care about having my code not return nothing. You roll a die, what did you get? Nothing. Right? Because if you use this algorithm, let's say you roll a 1, you subtract out 1/3, and you subtract out 1/3, and you subtract out 1/3, and you end up with 0.01, then neither of these 3 events will take place. Right? Because it's when it goes negative that it activates, right? So if I rolled a 0.1, you subtract 1/3 from it, that's a negative number, therefore the first event occurred. Okay? Is this CPP stuff or is it consistent with other languages? Floating point numbers are pretty consistent with other languages. You can't represent an infinite precision, right? Like, there's literally not enough memory to do infinite precision because it's infinite. It requires infinite memory. So sometimes people will hold numbers like this instead. We've got a fraction, because then you don't have to convert it into a infinite decimal. So if you hold it as a fraction, then you start with 3/3 and you subtract out 1/3 and you get 2/3 left, right? And then you can avoid some of these rounding errors. But in general, it's just good to get used to working with rounding numbers. Never expect the rules of algebra to hold, all right? So like rules of algebra. Okay. X equals y means y equals x. Don't expect that. 1 plus 2 equals 2 plus 1. Don't expect that. It might not. So with floating point numbers, like, they're all approximate and they're all, if you distribute, 3 times 1 plus 5, we would expect that to equal 3 plus 15. No guarantee. Anytime you see an equality in a floating point number, there should be a giant, like, what if it's not, What if it is, but it isn't? What if I add up these numbers two different ways and I get a slightly different number? Equality on floating point numbers only works when they are exactly the same. And so usually what you want to do for equality is you want to give it an epsilon value. And say if it's within this epsilon value, then they're equal, or something like that. Okay. Yeah, floating point numbers are inherently error prone. And so some people just like using fractions instead. Let's make it a rational. Let's make a rational class, the numerator and a denominator, and every time you do a subtraction or an addition, it works with the completely normal integer, numbers, and that works as well as you don't have, subtract out 1 over 117 or something like that. Okay, so word of the wise: never trust a floating point number. Okay. All right, so again, here's the difference between a probability and an odds ratio. An odds ratio is your ratio of winning versus losing. Okay. And that's when you have odds against. 4-to-1 odds against means you're 4 times more likely to lose than to fail. Odds 4 would be 1-to-4. I say there's 1-to-4 odds for Twilight Sparkle winning. That means she'll win 1 time for every 4 times she loses. And the reason why they do this, by the way, is so that's how you pay out your bets, right? So if you've bought a ticket on Twilight Sparkle and you put down $100, let's say you put down $100 on Twilight Sparkle at 5-to-1 odds. Then if it wins, they pay you back $500, right? So that's how the odds ratios are used for payments, and that's why they hold it that way. Yeah. Is that class already an STD? What class? Float? We're just talking about floats, man. It's not an STD. It's actually just a primitive. It's part of the language. Yeah. Rational? Yeah, I think there is actually. Get ratioed. So, yeah, there you go. Okay, so do you guys understand? Odds ratios. That'll be your quiz question. So let's take a look at the last quiz just before I forget. Let's go here. Okay, so what is the running time of this function? All right, so we're going to use the master method, the master theorem, whatever you want to call it. Code check, see if there's a match at midpoint if not searches the left and right half. Okay, so base condition, midpoint is halfway through the vector. If we got a match, return true. Otherwise, if there's a missing parentheses there, but whatever. It's not gonna. The running time is 0. It won't compile. Let's fix that real fast. Okay, so. If the vector at midpoint is less than x, then we search to the left. Otherwise, we search to the right. So there are 2 subroutine calls. So A is 2. Each subroutine call gets half the original vector. So that's 2 because it's the denominator, 1/2. B is the denominator, it's 2. And then the amount of work done at each level is like 1, order 1. So it's into the 0th power. So C is 0. B and A are both 2. The log base 2 of 2 is 1. 1 is greater than 2. So it is into the 0th power log n. So in order log n. Okay. Counts as 2 even though only 1 runs per call. For A, then it's even lower. It doesn't matter. So it'll be below 1 then. It doesn't matter. The point is yeah, it'll be log n. It'll be log n. Okay, what is the running time of this algorithm? This is binary search, by the way. So it's the number of levels down it's going to go is log n. And it does no work, essentially. It does 1 bit of work at each level. Okay. So what is the runtime of this algorithm? It returns the sum of the elements of vector between min and max. Base condition, midpoint is there. Returns 2 subcalls. So it does 1 operation, order 1. So this one is going to be order n because it does 2 subcalls. This one does 1 subcall. All right. So A is 1 on this one, and B is 2. For this one, A is 2 and B is 2. So this is order n. Okay. Okay. Yeah, you're right, Frisbee. You're right. This one, A is 1, B is 2. This one, A is 2 and B is 2. And both of these are bigger than C, and so that's what we got there. Okay. So, events are going back into probability. Something like rolling a die, flipping a coin, that kind of stuff. Usually, we talk about independent events, but events don't have to be independent. All right. So, like if you get hit by rain, which is apropos for right now. If you get hit by a raindrop, the odds of, it's not random. I mean, it's random, but it's not independently random. If you get hit by a raindrop, your odds of being hit by another raindrop in the near future is going to be higher. You know what I'm saying? Like, it's not just like, oh, if you just go outside during the year, you have a 1 out of 1,000 chance of getting rained on. Yeah, it's not independent. It's not like just every time you go outside, God rolls a 1,000-sided die and hits you with a drop of water. If you get hit by a drop of water, your odds of getting hit by another drop of water is much, much higher than if it was a clear day. You know what I'm saying? So. You guys understand this? Like a die roll is independent. Getting a a 5 on a craps table doesn't mean you're going to get a 5 again. There's something called the gambler's fallacy where, if you rolled a 5 on craps and then you roll another 5 on craps, people are like, oh man, I'm going to bet on 5 because it's come up twice. Or they say, I won't bet on 5 because it's come up too many times, it won't come up again. No, all that's nonsense. The odds of getting a 5 is exactly the same as what it was before. Okay? It's due to get a 7. All that is nonsense. It's complete nonsense. The odds are the same every time you make a die roll. It's the same odds. It doesn't change based on past results. Okay? I'm on a roll. I'm due to win. It's so stupid. And what makes craps like really terrible? One of the nice things about craps is actually its odds aren't that bad for optimal play. But rolling boxcars, pays out at a 30-to-1 ratio. The odds of getting a boxcars is a 6 on one and a 6 on the other is 1/6 times 1/6. There's one possibility out of 6 that you win on the first die. There's one possibility out of 6 you win on the second die. So the odds of this are 35-to-1. Right? If you have a 1 out of 36 chance of winning, that means you have 1 out of 36 possibilities, 1 of them win, 35 lose. And so they pay you 30-to-1, but the actual odds are 35-to-1. And so it's just a bad bet. There's literally no reason to ever bet boxcars if you're trying to make money. I mean, I guess if, I don't know, you're trying to impress James Bond or something, you bet boxcars and it hits boxcars, and James Bond's like, oh, I see you are an expert gambler. You're a master of the game of Baccarat. No, there's no such thing. Drives me crazy. Can't imagine me at a casino now. Yeah, it's because casinos are not fun if you know probability. Because you're just like, that's a bad bet. Why would you do that? On average, you're going to lose money. Like, is it, like, a lot of people are like, but it's fun. It's like, is it fun to hand over your cash to a casino? Like, I could just go over to the casino manager right now and be like, yo, here's $100. And he would take it. I don't see that as fun. I'd rather go to a steakhouse or something, you know. Like, the steakhouse at the casino's fun, you know. They usually have pretty good food, you know. And a lot of casinos, like, have pretty reasonably priced food because they want people to come there for the food and stay for the gambling. So there's that. You know, Chuck Chansey Casino used to have this amazing buffet. It had all you can eat crab legs and stuff. Like what? You know, it was like $20 a person, you know, and had this incredible. So like my wife and I would go up once a month to Chuck Chansey. And would I gamble? Hell no. It's just like you're on average, and that's how you have to think of these things. On average, you're just handing them money. Sure, sometimes you'll win, sometimes you lose, but you're going to lose more than you win on average. And so you might as well just cut out the middleman and just hand them the cash and leave, you know? And then you save 8 hours of your life. You could spend 8 hours on the slot machines losing your money, or you just walk up to the manager and be like, hey, here's my life savings, take it, and then leave. And now you got 8 more hours of your life to play video games or something, you know what I mean? It's most gambling games are utterly pointless. Like, it is, from a mathematical perspective, if you're playing slot machines that have a payout rate of 95%, that means for every dollar you give them, they give you 95 cents back. You give them $1, they give you 95 cents. That's how mathematicians think about these things. That's how you abstract the gambling. Here's $1, and they're like, oh, thank you for the $1. Here's 95 cents. Would you like to play again? Yes. Here's $1. Okay, here's 95 cents. Why on earth would you play that game? It's fun. It's not fun to lose money. I don't know. And like I said, if losing money is fun for you, just short circuit just give them the money. Here you go. Here's $1,000. Have fun. That was fun for me. Wow. Here's $1,000. So much fun handing money to large casinos. Save some time. Go watch TV. Hand them $10,000 and go home. You got 8 hours of your life now. So people hit once, then get addicted. Sure, because you go up and down, and that process of uncertainty is fun for people because you don't know what's going to happen. Yeah, mathematically, I can tell you what's going to happen. On average, you will lose money. That is the mathematical reality. Is on average, you lose money. And sure, you win some and you lose some. You don't know what's going to happen, but mathematically, I can tell you what's going to happen. On average, you hand them $1, they hand you 95 cents, and they will play that game as many times with you as you want. Now, there are some games that are different. Poker, obviously, it's not random. I mean, there's a random element to poker, but poker is not a random game, and that's why poker is interesting, right? You have a feeling most people are not good at math? Yeah. Do you know how much money the California lottery makes a year? The lottery is a purely random. It's a purely random thing. Like, there's no strategy. You hand them $1, they hand you 95 cents. It's actually probably worse than that. California lottery odds. every state lottery offers terrible odds. So 63%. So you hand them $1 and they hand you 63 cents. Cool. Cool. That's how mathematicians think about it, and that's why lotteries, I consider a tax on people who are uneducated. Right? Did somebody say poker? Yeah. So Nico plays poker, and poker is an interesting game because it's not like, Nico, what percentage would you say of luck poker is? Like, if you always get dealt bad cards, you're going to lose, right? Like, if you just never, ever get a good hand, like, unless you can somehow bluff people into, like, folding for you, I guess. I don't know. Yeah, I guess. But, I mean, at some point, somebody's going to call you and you're going to lose, right? So, I don't know. Luck doesn't exist in poker. Okay, well, there you go. But to me, like, you always get bad draws, then you're going to fold a lot, and the ante will kill you, you know. The only way you can make money is if you could somehow bluff people into thinking you have the best hand ever or something. I don't know. But fold 50 hands straight, yeah. Like, there is a luck element to poker, because you're randomly dealt 2 cards, right, in Texas Hold'em. And so there's a luck element, but it's not a luck-based game. It's a skill-based game. It's about being able to read other people's faces and look at the cards and look at their betting patterns and things like that. So poker's exempted from this. And then blackjack is also an interesting case. So have you guys ever heard of counting cards in blackjack? There's so much about it, especially in math, yeah. Have you guys ever heard of counting cards in blackjack? So, what deck of cards are in here? I don't. You guys have all seen a deck of cards, right? So, in blackjack, traditionally blackjack was, in The Hangover, yeah. Mm-hmm. My dad used to do that, by the way. My dad used to count cards in Tahoe. He was stationed in the Air Force Base in Travis, I think. And he and his buddy would go up to Tahoe every, weekend or, a couple weekends a month. And my dad would count the cards. But my dad hated betting because he didn't like putting his hard-earned money on the table and watching somebody just collect it. He just hated that feeling way more than he liked winning. So my dad would sit there and count the cards, and his buddy would sit there and drink, and he wouldn't even look at the cards hardly. He's like, yeah, hit me, and they won over and over and over again. And the managers would come by and be like, how is this guy counting cards? Because he's not even looking at the other people's cards. This guy is like either some sort of genius or something, but he's like very social and he's tipping everybody and everybody loved him. He was just like one of these very high charisma people. And so I guess the managers was like, I don't know, like people like playing with him, and I guess on the net we're making money, so they never kicked him out. And so even though they knew somehow he was cheating, it's not actually cheating, because counting cards is not cheating. It is not illegal. Like, if you were to swap out the cards or something, that's cheating. Counting cards is just strategy, right? Casinos don't like it when you do it because you can win. But they could never figure out how this guy was counting cards, and it was because he wasn't. My dad was. And so when you have a single deck of cards for blackjack, there are certain deck states, the cards that are remaining in the deck, that favor the player. Due to the way how blackjack works, it's not a symmetrical game. Blackjack has 2 points of asymmetry. First, if the player blackjacks, they win immediately. Right? So if you hit blackjack, they pay you out 1.5 to 1. And if you bust, it doesn't matter if the dealer busts. You've already busted, and they've already collected your money. And so, by and large, it's a symmetrical game between the player and the dealer. You're trying to get closest to 21, but there are these 2 points of asymmetry. And because of that, if the deck remaining has a lot of face cards, 10s, and a lot of aces, the odds of getting a blackjack will actually go quite high. And if you're counting the cards, if you remember what cards are remaining in the deck, then you can signify, like you could signal your partner, which is what my dad would do. He would tap him on the back and be like, hey, the deck's hot right now. He wouldn't say this. He would signal him by like poking his back, and then the guy's like, you know what, I'm feeling lucky right now. Let's bet $100, And he would start betting $100 a hand in blackjack. automatic payoff. Blackjack, automatic payoff, you know. And by doing so, you can actually tilt the odds in blackjack into your favor. And so casinos in recent years have come to use more decks to make it harder to count. My dad played bridge when he was a kid. My whole family is very competitive when it comes to gaming. And so, like when I was a kid, we'd play Uno, and my grandfather would sit next to me, and he would hold on to a draw 4 until it got reversed my way, and then he would draw for me. You know, like if I was winning. You know, like this is like when I'm 4 years old. When I'm 4 years old, he's not playing it because I'm in the lead. I've got Uno, and he just waits for it to get reversed so he can draw for me. You're like pretty brutal, like Uno play, you know, on a 4-year-old. You know, and I would get all angry and frustrated, like you know. Yeah, he's like, I'm not gonna let you win. You know, we're playing to win here. And then we would play Hearts. We played a lot of Hearts. That's my favorite card game is Hearts. And yeah, same thing. No mercy. And from playing Hearts, I learned to count cards, because Hearts is a trick-taking game, and you have to pay very close attention to how many cards are left in each suit. And so I would be like, all right, the 7 of clubs and the 10 of clubs are still out there. I've got the 8 of clubs, and I know only one person has clubs. So if I lead the 8, he's going to play the 7 and go under it, then I'm going to take the trick. I'm going to be stuck in the lead. So I'm going to play the 6 instead. Then he'll play the 10, so he'll take it, and then he'll probably lead the 7 and force me to take the 8. So if I play the 8, he'll take the 7. And so then I'm like, all right, how many spades have been played? When is the queen going to come out? And so you pay attention to every card, and you memorize it. And so my dad played bridge, which is a similar trick-taking game. And so my dad could look at it, he would just glance at the table and be like, all right, there's 3 kings, there's 2 jacks, and 3 aces left. Like, he would know. You just watch the table. And they'd reshuffle, and his mental counter would reset, and every card comes out. My dad's like, all right, there's the 2 of hearts, there's the 2 of spades, there's the 7 of diamonds, bloop, bloop, bloop. And he just had an array in his head and crossed them off. And then once the deck was optimal for betting, he'd tap his buddy on the back. Buddy would up the ante, and they made money every weekend. And the dude never cut my dad in on the money. He would pay for my dad's hotel room and food and stuff like that, but the dude made all the money, and my dad would, like, just, you know, had the free food and free meals and entertainment and stuff like that. So tried counting in hearts. Yeah, it's just, you just have to play a lot of card games. And so my dad told me these stories when I was growing up, and so when I turned 21, I'm like, I want to go to Vegas and count cards. And I practiced. You can go to websites and practice counting and things like that. And there's ways to do it. Like if you can't keep track of every card, then there's algorithms you can use. Like every time a king comes out, every time a face card comes out, you subtract 1. Every time an ace comes out, you subtract 2. Every time a 2 comes out, you add 2. Every time a 3 through 6 comes out, you add 1. And so you just maintain a running count in your head. And when the score gets high, you raise your bet. When the score gets low, you drop your bet. But also, and what I found when I was playing counting cards in Vegas, like if you know there's like if it's a poor deck, if there's a lot of low cards, I was actually playing differently, because it's like I have a 14, the dealer's showing a 7, hit 2, hit 3, hold. You know, and the guy next to me is like freaking out. He's like, "What the hell? What the hell? You hit on a 14?" I'm like, "Yeah." You know, and I got a 16. And you hit on a 16? I'm like, "Yeah." He's like, "Man, you're stone cold, dude." But it was just because I knew what was remaining in the deck was just a bunch of tiny cards. There was a small chance that I was going to bust. There was a few bigger cards left, but I knew like the deck was just all like 2s, 3s, and 4s basically. And sure enough, the dealer flipped over his 17, and I beat him. Right, and so, you know, it's, you know, blackjack is not exactly a random game. There's randomness in it, but it's not a random game, because it's not like they reshuffle the deck of cards every time, right? They have a deck of cards, and as the cards come out, you start learning things about the deck, and so it's not just random. You're not getting a random card from 2 to ace to king, you know? You're not getting a random, there's a deck, and so those decks are 52 cards, and as you play, you start learning more and more information about what's remaining in the deck. So it's not purely random. It's not like craps, which is a purely random game, or a slot machine. Right? So, and I don't trust slot machines to be purely random either. By the way, when I was working doing virtual reality game development, a slot machine company came to us and wanted us to make a virtual reality slot machine. So basically, the notion was the player would sit inside of a virtual world, and they would run around. Like, we had this mecha game where you'd launch rockets and lasers and stuff like that. You'd walk around, you'd explode buildings, and you would collect like pieces of a prize, right? So you'd get like a third of a car, and then you walk around some more, and you get the second piece of the car. And you're like, oh my gosh, I got the second piece of the car, but you'd never get the third piece of the car. Like, it was rigged. Like, it looks random. I got 3/4 of a hotel room, and time ran out. And that was the design. The design was you get people super excited, like, oh my gosh, I am one piece away from winning a car, and then they just never get the car. It looks random. It looks like you're blowing things up, and look, you get a piece of a hotel room, you get a piece of a car, you get a piece of $1,000. It's like playing the Monopoly game at McDonald's, right? I have collected almost all of the railroads. I've got 3 out of the 4 railroads. I am so close to winning a train or whatever it is they sell. And craps, there's certain ways to roll dice. Yeah, if you're a dice mechanic, then that's a different thing. And I practiced that for a while. Like if you under carefully controlled circumstances, I can roll a d20 and have it land within one number of the right answer. I don't cheat during D&D, Nico. You don't have to worry about that. But there are D20s that are called spin down counters, and so for a spin down die, the numbers are not like on a normal D20. It's like a 20's here, then a 1's next to it. So even if you can get within one die face, the good number is surrounded by bad numbers, so it doesn't benefit you that much. But a spin down, do you see that? All the good numbers are on one side. And so I got to the point where I could roll a spin down and constantly hit in D&D if I cheated, which I don't, because it defeats the entire purpose. But and they have these like giant spin downs and things like that. 55. How big is that? Yeah, look at the size of that. You see that? This is a regular D20. It's a massive D20, and that's not a spin down. That's not a spin down counter. Spin downs are have all the numbers next to each other. These are spin downs though. And so with a spin down counter, you can absolutely dice mechanic and get good numbers every time. So McDonald's Monopoly game got busted for being a scam. Yeah, because it makes you seem like you're going to win. Because it seems like it's just random. I'm just getting random properties, and you keep eating more and more Big Macs and getting fatter and fatter, and then you realize that just Boardwalk never comes up, and the B&O Railroad never comes up. And yeah, so I don't trust slot machines at all, especially because they're all computer controlled now. And so, yeah, I will play a slot machine just to say that I gambled in Vegas. Like, it's kind of this weird thing that I do, a weird personality quirk. Like, I'll go to Vegas and I will take a single quarter and I will play a single play on a slot machine and be like, there, I've gambled. And then I just don't gamble the rest of the time. Not like I've been to Vegas since the pandemic began, but, we used to go to Vegas every year and I would gamble. Because people are like, you went to Vegas and you didn't gamble? So now I can tell people, yeah, I gambled. How much did you lose? A quarter. Wow, good job. Yeah, thank you. I was a very successful gambler in Vegas because I only lost a quarter. And sometimes it would be a nickel. Just put in a nickel. There you go. So, gambling and drinking. Yeah. And some people do that because they give you free drinks when you're playing the slot machine. But if you do the math, it's just buy a drink, rather than losing money in the slots. Yeah. Yeah, you put in a penny, whatever. For me, it was usually a quarter because I'd usually have quarters on me. Put a quarter in. There you go. I lost. Once I did that at Chuck Chansey. I put in a nickel just to say that I gambled, and I won $20. Like, it was a what's the odds payout on that? It's 20 to 1 for $1, so it's a 400 to 1. I hit a 400 to 1 jackpot or whatever. on a single nickel. So it's like, it paid for my all-you-can-eat crab legs. Look at that. So, okay. So it gets more complicated when you start talking about 2 dice. Okay. So if you roll 2 dice, then you have to think about all the different ways one of the dice can come up and the other dice can come up. And it looks something like this. So you can roll a 1 and a 1, a 1 and a 2, a 2 and a 1, a 1 and a 3, a 2 and a 2, a 3 and a 3. And so if you roll 2d6, 2d6 has a kind of a bell-shaped curve almost. It turns into a bell curve. 7 is the most common result on 2d6. That's why craps is a 7 or an 11. In Catan, the thief comes out on a 7 because it is the most common die roll. It's not that common. It's still only a 1 out of 6 chance. So a lot of people think that the odds of a 6 or an 8 are actually higher than they are. 6 or an 8 come out 5 at it. So about 1 out of 7 times you'll get a 6 or an 8. So if you're playing in Catan and there's a 4-person game, it'll probably go around twice, but before you get a single one of your 6 or 8s paying off. Like people tend to overestimate how often a 6 or an 8 gets rolled in Catan, but they are the best spots because the odds of getting a 6 or an 8 is higher than that of getting a 5 or a 9, which is higher than that of getting a 4 or 10, which is higher than that of getting a 3 or 11, and 2s and 12s are the worst tiles to have in Catan. They just don't come up that often. So we'll stop here. Your quiz will be on odds ratios for today, and just convert between a fraction and odds ratio, and we'll talk more about gambling and bringing down the house. Next time. Is Nico still here? No, Nico's still there. Yeah, okay, I'll mention bringing in the house just because it pisses me off. So there's this book or movie called Bringing Down the House. And it's about the MIT Blackjack team. And the book says only MIT students are capable of counting cards in blackjack because only MIT students have the level of calculus and advanced mathematics necessary to count cards at blackjack. And I was like, eh? Eh? You do not need calculus to count cards at blackjack. I'm sorry. You don't. You need to play a lot of card games when you're a kid. That's all you need to do to count cards at blackjack. And so what the Nico, have you heard about this? The MIT Blackjack team? So every weekend or every month, something like that, they would fly from Boston to Vegas and they would play blackjack the whole time. And they would make quite a lot of money doing it because they were counting cards. And so they counted cards. It wasn't their movie yet. Mm-hmm. And they counted cards, but they hid the fact they were counting cards. They had like Wi-Fi communications and things like that. So like the way that casinos detect that you're counting cards is that you win a lot, right? And not only that you win, but also that you fluctuate your bets. So when the deck gets good, when there's a lot of jacks and aces and things like that in the deck, you go from betting $5 a hand to betting $100 a hand. That's a clear sign that you're counting cards. So what the MIT Blackjack team did was, dude pulled down his pants to show he wasn't cheating. I haven't seen the movie because I read the book, and the book pissed me off enough that I didn't watch the movie. So, because it's like, it's just so like self-gratifying to the MIT people. It's like, you know, look, they had a cool system, and I will give them absolute credit for that. But claiming you need to know calculus to count cards in blackjack, I'm like, no, A, you don't, and B, everybody does calculus, bro. Like, it's not special. So what they do, though, is they would have a person sitting at a table, and they wouldn't fluctuate their bets. They would just play $5 hands. They'd play whatever the minimum bet was. And then when the deck got hot, they would signal by some, you know, Wi-Fi or, you know, some hand signal or something. And then a person would blow in wearing a big Texas hat, like, I'm feeling lucky tonight. $1,000, $1,000, $1,000, $1,000, makes a bunch of money. Have a good night, tips the dealer $20, walks away. And so that person doesn't fluctuate their bet, and the person playing at the table doesn't fluctuate the bet. And so the reason why it was a team was because they would have a person sitting at every table in the casino waiting for the thing to get hot. And so you'd have all these spotters, essentially, just mentally counting cards and waiting for the thing to get hot, and then they would signal, cuckoo, cuckoo. And then the guy in the big Texas hat would come in and be like, yo, let's do this. $1,000, $1,000, $1,000. Walk away. And so by doing that, they were able to always have some hot table somewhere, and they would and the person would always bet $1,000, whatever the table limit was. And then it wouldn't show any signs of counting cards. And they did this for a while until the casinos obviously caught on, because nobody wins consistently, right? That's, it's very suspicious when you win consistently. And so they ended up all getting banned from Vegas, right? So it's not illegal to count cards, but the casinos do not have to allow you to play. So they had their faces entered into a facial recognition database and were asked to leave under no uncertain terms. And apparently, according to the book, they were backroomed a bunch. They were hauled into the back and beaten with clubs and things like that. So then they moved to different areas and riverboats and things like that. But I was bringing down the house, or whatever the 2003 movie. Romantic? No, that's not it. Queen Latifah? No. Blackjack. The inside story of 6 MIT students who took Vegas for millions. Yeah, I've read that book. It's Friday night and you're on the red eye to the city of sin. Strapped to your chest is $500,000. You got 25,000 blackjack chips. You got 10 fake IDs. You're being investigated and followed. The IRS is auditing you. Blah, 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 blah. An eccentric mastermind, a former MIT person. They made more than $3 million from Vegas. Okay, so the book is called Bringing Down the House. I don't remember what the movie's called. This movie's why people think computer science people are genius. Yeah. What is the movie based on it? 21? Was that it? Okay. All right, so that's it for today. Hope that was at least entertaining for you guys. You learned multi-threading earlier on. You learned about gambling and counting cards and stuff like that later on. Poker and counting cards. Yeah, exactly. So we'll talk more about probability next time. All right, thanks everyone, and I will see you in 2 days. Peace out. On Thursday. I think so. I think we had class on Thursday. Do we not? Anyone know? No class? All right, I'll see you next week then. See you.